dynamic analysis of 35 per meter of span composite girder. Now coming to introduction slide. So introduction, the high speed train affects serviceability of bridge as well as the structural performance. So basically bridges are designed for both checked for serviceability as well as the structural adequacy of the girders. High speed also affects the passenger comfort. RDSO design standard bridges are fit for a speed of 125 kmph as I told earlier. Currently bridge rules which provides only an impact factor called CDA for the dynamic effects of the plane loading. CDA does not consider the maximum floor acceleration which may cause the loss of rail wheel contact. So it may, vehicle may derail also on this account. As per Eurocode, the maximum bridge deck acceleration shall be restricted to 3.5 meter per second square for ballasted decks and 5.0 meter per second square for unballasted decks. So this, while designing the static, while we are doing the static design, these are not checked. We don't check this deck acceleration in the rotation and vertical displacement on account of high speed. Next slide. So what, there is no Indian, this is a very new topic, no IRIS standards are available, so we took up methodology adopted as per UIC 7762R. Dynamic analysis carried out by a numerical method using the finite element modeling of the composite girder. Here, the composite bridges considered in this study consist of concrete deck and steel girders. They were connected together with the help of shear struts, so these are into composite action because it's a composite girder. So we have connected with shear struts, the connection between both these shear struts. Train loads considered in the analysis, Vande Bharat train loading T18 at maximum speed 224 km. And we did this up to 40 km. So next step. So here, how did the load was modeled? Train load has been modeled as a series of moving point loads by neglecting the inertial effect of the moving train mass. What I want to say is the train was not modeled. It is very difficult to model the train. So we left that part and results, the impacts are not much if you model the train also. The point loads have the same magnitude and spacing as per the RDSO standard. Damping is considered 0.5% recommended by Eurocode. Track regularities and vehicle imperfections have been considered by multiplying the results with a factor of 1 plus side double dash as recommended in Eurocode. This is very complex mathematical formula. Only thing I want to know, why to tell, in track irregularities we don't model. Whatever the results come out as a numerical this modeling, we multiply the results by 1 plus side double dash to account for this track irregularities and vehicle imperfections. Next slide. Linear motor time history analysis has been performed for train loading. Free vibration eigenvalue analysis has been performed and number of modes up to frequency of 30 Hz or 1.5 tons of the first mode as per Eurocode has been used for analysis with at least 3 vertical bending modes included in the analysis. In the coming slides I will take up this what is mode. Next. This is a performance evaluation criteria. On what criteria we have checked this dynamic analysis. First criteria is criteria for passengers' comfort. Here, vertical acceleration inside the coach to ensure passengers' comfort is limited by limiting vertical displacement of the bridge. We have to limit the vertical displacement of the bridge so the acceleration in the coach remains within these limits. If you want to gain the level of comfort at the level of very good, the vertical acceleration has to be limited to 1.0. For good it is 1.3, for acceptable it is 2.0. You can allow acceleration up to 2.0 if you want to comfort level up this acceptable. Next. For simply supported bridges with 3 or more spans, limits on vertical displacement shown in figure ensure very good level of comfort inside the coach. This graph is for very good level of comfort. That is 1.0. In the preceding slide, it was 1.0. For that, this graph has been, this template has been developed. Next is for other level, the values of L by delta. L by delta is shown on the y-axis, and this speed is shown on the x-axis. So, when we want to change the level of this comfort, you want to go for acceptable level, then what you do? We divide the L by delta by BV. This is permissible vertical acceleration as per the passenger comfort criteria. For simply supported or continuous bridges up to 2 spans, the value of L by delta shown in the figure is to multiply it by a factor of 0.7. So this is a graph between L by delta and L. L is a span. So whatever the vertical displacement from comfort point, passenger comfort, that has to be within this envelope. See, for different speeds, this envelope has been developed by drawing a graph between L by delta and L. Next, running safety of the plane. This is now we go to safety part. First was the serviceability. This is comfort. Now the safety. In safety, we have to again limit the vertical acceleration, vertical deflection, and in rotation of the bridge. For both EN and UIC codes specify almost similar limits. Now in safety, first is the vertical displacement. Excessive vertical displacement of the deck leads to significant change in the horizontal and vertical track alignment that will increase rail stresses. Additional rail stresses will be developed in the rail, so that may affect the running safety of the train. So limit is here as per EN code is L by 600 and as per UIC is L by 800. Thus a conservative, we have taken a conservative value of L by 800, but not larger than the limit specified for passenger. Again, that has to be within the limit specified for the passenger comfort. So there are two checks. We have one check is for safety, one check is for comfort. Next, here vertical acceleration, limit of vertical acceleration are specified. A limit of vertical acceleration is required as the maximum vertical acceleration affects ballast stability by losing their interlocking. So consolidation of the ballast gets disturbed if you exceed these limits. Also, excessive vertical acceleration leads to an unacceptable loss of wheel-rail contact. This is a very serious issue. If we allow more acceleration, then wheel contact may be disturbed, and this may lead to derailment. So values are for ballastic track is 0.35, for slab track is 0.5. Next. This is an end rotation. So the Euro code indirect, this is the indirect limits on the end rotation. Like controlling the longitude, you control the longitudinal displacement, then end rotation will be controlled. Here the governing is the height. You lessen the height, this height depth of the girder, the displacement will be lesser. It is 8 mm when there is a Labra track. So to take the rail structure interaction, the limit is limited to 8 mm. And when there is no interaction, means there is no Labra on the bridges, then limit goes up to 10 mm. Next. So now coming to actual what we did in the modeling, these are the parameters: clear span, effective span, grade of concrete, steel, property, dead load, and SID. Next. Now coming to modeling, we did the 3D FE model of this superstructure was developed in Mirage software. We used this wizard, Mirage software wizard, assuming the support to be rigid. The train loading was considered as a series of moving wheel loads along the track. As effect of mass of train, suspension and track, irregularity can be ignored. Initially I said we ignored these parameters. Yes. The flexibility of ballast was ignored, however mass of the ballast is considered. The effect of bearing type, substructure and foundation was not considered in the analysis as it is negligible. Next. This was Mirage, is the Mirage model, this was the cross section. Next. This was the 3D view. The girders has been divided into large number of elements with maximum size of 0.5 meter. To model the composite behavior, steel girder and concrete slab have been connected rigidly by shear studs. The mass has been considered in accordance with the RDSO standard diamond. Next. Modeling of moving, how did I model the moving train load? Train load has been modeled as a series of moving point loads. The point loads have the same magnitude and spacing as per the RDSO standard. The train is assumed to move along the straight path with a constant speed, and the speed was increased from 1 kmph to 250 kmph. This entire this analysis was done up to 250 kmph with the increment of 1 kmph. This was the train. This was the modeling of load. These are the axles. This is the axle load on the y-axis. It is nearly 16.5 ton. So it is axle load of the train set, and these are the axles. Coming at a center point at a speed of, this is a typical chart for a speed of 140 kmph at center point of the girder. So these are the axles coming at different time intervals. Next. These are modes by when we model the bridge, when we find that there are about 20 types of modal vibrations in the girder. There are mode 1 when crest, there is a single crest in the girder. There are two crests in the girder. Girder is vibrating like this. There are two crests in the whole span. And third is mode 3. So mode 1, mode 2, mode 3 are prominent modes which decide the values of this vertical displacement in rotation and deck acceleration. So I have shown the mode 1, 2, 3. Percentage of participation is 80% in case of mode 1 for translation in Z, in the Z axis. And for rotation, it is mode 3, which with mode 2 in rotation, in Y axis rotation is 56.63 by mode 2. Next. So this is the summary. Result was like this. Maximum vertical acceleration was 3.336. Maximum vertical displacement is 0.007. Maximum end rotation 0.0006. Maximum amplification factor, that is CDA 1.150. This was the result. Next, graphically we have shown like this. Variation of maximum of the vertical acceleration at 2 points, L by 4 and L by 2. What we find that for in the case this at L by 2, it is nearing at a speed of 140 km. It is within the limit. The red line is the limit. It is nearing that limit, but it is safe. Next, variation of maximum of the vertical displacement L by 4 and L by 2 with the speed of 10. It is vertical displacement. Vertical displacement is considerable within the limit. There are two limits, one for running safety, that is in blue color, and in red, it is passenger comfort. So the results were well within those limits. Next. The variation of coefficient of dynamic augmentation. So red line is the dynamic augmentation as per this CDA formula given in the bridge rule. So what is a very interesting result? At a speed of 140, nearing 137 kmph, the amplification is 1.10. As per bridge rule, it should be near 0.4. So at 2 points, it has exceeded those limits. But it doesn't mean that our bridges are unsafe, because here axle load is only 17 ton. We have designed the bridges for 25 ton. So that takes care of this anomaly. Next. This is variation of end rotation support point, speed of 10, that is well within the limit. Conclude. Yes. Next. RDSO standard composite girder fit as per permissible criteria as per this UIC, as I told earlier. Coefficient of dynamic augment is 1.15 times for the speed 140 km at 205 km. This is much greater than RDSO formula. Further investigation required to carry out by determining the CDA for other passenger train loadings and 25 ton negative. Thank you.
The last paper of this session is by Sri K.V. Ramamega, and
there are two questions. One question is, you have shown a graph of CDA variation with respect to speed and compared it with the static CDA as per these rules. How is the dynamic CDA determined as shown in the graph? I think Sir DG sir has sent this. Sorry, name is not there, so okay, sorry sir. So what when we do the modeling, after that we start the simulation. First we test the loads under static condition. There is no speed. We find the stresses. The result comes in the form of stresses in the member. Now we start running the loads. At all speeds, stresses will increase. So the increase in the stress is due to CDA. So now CDA is correlated with the increase. Suppose first time under static condition the stress is 100. Now the stress is increased to 150. So 50 part is due to this CDA. So in this condition CDA is 0.5. So this way it is determined.
Running of load.
Under running of loads.
Under running of load. That also is done by the model analysis. I mean there is no physical work at site.
No, sir, it is only computer simulation.
Only computer
Yes sir. For validation we will do the this instrumentation later on. Yes, that will be done.
Because I worked in the research section in the 1970s in RDSO,
Sir,
and we were doing the impact studies
yes.
on various girder bridges, field trials later, when the impact for
Okay, CDO formula was generated, then developed.
Earlier it was 20 upon 40
Yes,
plus
sir.
S. It was changed sometimes in 73, 74.
Yes, I have gone through that paper also, sir. It was a long done study. Yes. Sir, there is a second question. What changes in parameters for bridge design are required, or any study undertaken for speed potential of 200 to 220 kmph for Vande Bharat train potential? The question has been asked by Rajesh Wankar, my batchmate. What we have done, for dynamic analysis, we need three parameters. This is vertical displacement, deck acceleration, and in rotation. So far, there is no IRS standards available for that. We have taken up a project with IIT Roorkee at a cost of 1.78 crore. They are doing the dynamic analysis of all 72 standard spans of RDSO. At the fag end, they will develop a guideline. They will define the limiting parameters, permissible values of these parameters, and we will go ahead. Like guideline will be developed at the end. Thank you.